as I said, the plus and minus charges are combined with the electric field line. This is something like this. We apply a tension to the string, and suppose with the tension, what will happen if I oscillate one end in the simple harmonic way? Then for the string, that makes a wave. Likewise, as I told you, when these two are connected by the electric field line, if one is oscillating simple harmonically, this electric field lines makes a wave like a string wave. Uh, I think you are familiar with this. Hmm? You are familiar with this because with a string we can make a wave. That wave, if the one end is hard, that will be reflected back. Hmm? So I think this type of thing is there in your gymnasium. So to do the exercise, it is very heavy rock. Since its mass is very heavy, that reflected wave is given shock to the body. Likewise, if one charge is oscillating, that makes a wave through the electric field line. That is how we generate the electromagnetic field. Electromagnetic field. In simply, people say to generate the electromagnetic field, people say a charged particle should be accelerated. It's correct because since it is oscillating simple harmonically, always it is experience an acceleration in the back and forth direction. Sorry, up and down direction. Then, similarly, the electric field intensity, electric field will be created in this direction. Electric field will be created in this direction. I think we have a nice animation in the internet. I will find it and let it show. I will share the screen for the moment. you see this uh, again, look, if the charged particle is oscillating, the connected electric field lines also makes waves. Is that clear, Kasun?
Yes, sir, clear.
Yes. So that is the basic of generating the electromagnetic field. And can you see the board?
Yes, sir.
Okay. Uh, I will stop sharing this. Uh, Simultaneously, if it is a electric field line, simultaneously it makes the magnetic field in the perpendicular direction. Perpendicular direction. If electric field is in this direction, the magnetic field makes in this direction. So we can show it later, uh, and how the magnetic field comes with the oscillating electric field. Uh, so that is how we generate the electromagnetic field. But the for the standing waves, standing waves, uh, this peak remains same, but this peak will move in the in one direction. So we can draw the maximum field line this way that will be moved in this direction. So if an electromagnetic field moves from one media to another media, M1 to M2, those waves penetrated this uh, distance is lambda. But from one medium to another medium, frequency remains constant. Frequency constant. If it is moving in this direction. But what will happen to the wavelength? 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 Wavelength is not a constant when the radiation is moving in one particular direction. Wavelength can be changed. That is why the speed of the wave is changing from one media to another media, because P equals F lambda, F remains constant, but lambda may change. Because of that, the velocity may change. Let's see how that behavior change the path of the radiation. First one,
Yes, sir.
am I audible?
Yes, sir.
Okay. This is a simple assignment for you. Maybe you can draw a scale diagram having a graph sheet. Uh, I will draw a rough diagram for you. Then you will understand how the propagation path of the uh, radiation, or simply we can say electromagnetic field, change when the media is changed. Right. So this is the an exaggeration diagram. This is media one. This is media two. Let's think the radiation is penetrating in this direction. I will use a black color pen. Then the wave fronts are arranged like this, having the same distance since the uh, media is same. Hmm? This width is same. Huh? So I'm not good at drawing. Maybe you can assume that these lengths, the distance between the two wavefronts are same. Here, uh, in this media, suppose as I told you, the wavelength can change, and still we don't know how much, but we can assume this much is changing. Then according to that, uh, we can draw it. We draw, suppose is this much. This is lambda 1. This is lambda 2. And according to this, the wave should be penetrated perpendicularly to this surface. Mm, looks like perpendicular. Uh, this is the transmitted, sorry, uh, penetrated radiation. This is the incident radiation. And because of this wavelength change, the path of the radiation should be changed. Did you understand, person?
Yes, sir.
How about the others? Because I explained it in a simple way. Uh, Himansha, did you understand?
Yes.
I can't hear.
Yes,
Himansha?
sir. Yes.
Okay. Then, if that is changing, we can quantify it, and that was quantified by the Snell's. That formula is called Snell's law. And the Snell had a property of a medium that is called the refractive index. Index. What is the refractive index? What is the definition of the refractive index of a media?
Ratio between Sine ratio between incident angle and
Yes,
refractive angle.
that's correct. I mean, with the velocity of the radiation,
Velocity of media over velocity of free space.
very good. Velocity of the media, not velocity of the radiation is in one medium divided by velocity of that radiation in free space. Uh, then for M1 medium, M1, let's say the refractive index is N1. N1 equal, let's think the velocity is V1. V1 upon C. V1 is the velocity of this radiation in M1 medium. For medium M2, similarly, M2 equal V2 upon C. Then this ratio N1 upon N2 equals V1 upon V2. I think the board is not clear for you. V1 upon V2. We know V1 equals frequency times lambda 1. V2 equals frequency times lambda 2. Then the frequency is a constant, and as a result, we can say the ratio of refractive index equals the ratio of wavelengths. So that is the quantification of these two. How much does it change? This is the amount of change is theta. Amount of the wavefront line change is theta, and So here this angle is incident, incident angle. This is I and this is alpha. Can you find alpha? This is alpha I. Can you find the relationship between alpha and theta? Alpha and theta. Awesome? Awesome?
Yes, sir.
What is the relation? Alpha, theta. Good. Because always the direction of the radiation is perpendicular to these wave fronts. So I will draw it exaggeratedly at the point of refraction. This is the medium interface. This is our incident radiation. This is our refracted radiation. And here we can draw a perpendicular line. Here also we can draw a perpendicular line. Anyway, the uh, amount of the deviation is theta, and we can consider this as I, this as alpha, and this is also perpendicular. If it is I, this is pi upon 2 minus I. If this is alpha, This is 5.2 minus alpha. Hmm. This is I, pi upon 2 minus I. This is also I. Am I correct? Person? Person?
Yes, sir.
This is I. This
Yes.
angle pi upon 2 minus
2
I.
minus I.
Then this is I. So this is alpha. Uh, no, not, this is not the alpha. Uh, this is alpha. I'm wrong. Then this is pi upon 2 minus alpha. So this angle is again alpha. And this is I, this is alpha, then alpha minus I is the theta. Alpha minus I is the theta. Then definitely that much the radiation will be reflected. And what did we prove? The Snell's law. With a scale diagram, you will be able to prove with a scale diagram this ratio equals to sine I upon sine alpha. Sine I upon no sine alpha upon sine I. And you can get this expression in 1 sine I equals n2 sine alpha. This is called the Snell's law. This is called the Snell's law. This is valid only for the radiation, not for the single stationary electric field line. Shall I write? Students,
Sir,
shall I write?
okay.
To start the next part, we have to have a good knowledge of the vector algebra. Uh, you know, in simply we say a vector is a thing having a quantity and direction both. So if we introduce a vector, we have to mention the amount of that vector, that is called a magnitude, and the particular direction. If there is no direction, if the quantity only is there, that type of thing is called a scale, scalar and vector. So in the vector analysis, uh, we consider the partial derivative with respect to x. Uh, if there is a function of psi x, uh, there is a difference between this. Can you explain what is the difference? If there are 2 or 3 variables here, x, y, z, also,
So upper one is partial derivative.
yes, it is called a partial derivative. What is the difference in an operation? In the operation, what are we doing? In the
No
partial,
idea, sir.
sorry,
No idea, sir. No idea.
in the partial derivation, we consider here we consider y and z are constants. Constant for the moment of that operation. But here we do not consider that. Sometimes x and y might have a relation. X and z might have a relation. But in the partial derivation, we assume the other variables remains as a constant. Clear?
Yes, sir, clear.
Yes. That is the difference between the partial derivative and the other conventional derivative. Now, in 1D case of vector analyzation, uh, we introduce the unit vectors in x, y, z direction. X, y is the direction. Unit vector in the x direction is denoted as I. Unit vector in y direction is denoted as G. The unit vector in z direction is denoted as K. There's a hat. The hat indicates that this quantity is a unit vector. What do you mean by unit vector?
Magnitude is 1.
Magnitude is 1.
Yes.
A vector having the magnitude 1. Uh, uh, then if there is a vector in x direction, let's say x can be expressed as the magnitude of x times I. Clear?
Yes, sir.
So similarly, y, this half arrow means it's a vector. In books, there are many ways to indicate vector x and line, and so my is the half arrow at the top. Both are same. Huh? So y is the magnitude of y times g. Uh, z is the magnitude of z k. And the operator in x direction can be expressed as uh, double upon double x I. This is for 1D case. But for the 2D case, if we consider x and y direction, the operator, gradient operator, this is called the gradient operator, double x I double upon double y j. For this is for 2D case. For 3D case, double upon double x I double upon double y j double upon double z k. For the 3D case. So the gradient operator, or grad operator. This is the and in the Cartesian coordinates. But if the considered coordination system is changed, this operation, the factor of the operations may change these factors. And for our convenience, we consider the cylindrical coordinates, spherical coordinates. It depends on our requirement to be solved. Right. Let's start from 3D case. If we can learn 3D case, there is no problem with one here. 3D. In the 3D case, for the Cartesian del operator or grad operator, symbolized as this. People call it as Their operator, operator. Clear? I will give some exercises, two examples. One, there is a vector field electric field having x 3x I 3 x squared y no, 5x squared y 9 x z minus 3z squared. This is in j direction. This is in this is k direction. Xz 3z squared. This is in k direction. So, this is a vector, and the second one is with the scalar p equals 3 2 xy square plus 3 xy z. My question is find this. This is the first question. What is the value expression? Second, now this is a vector. If you get the gradient of a scalar, it's a vector. Then we can get the dot product. C again dot product of D I will label the terms. This is called a gradient of V of V. This is called the curl of the gradient of V. This is called the grad of the gradient of divergence of the gradient of the V. Now find the curl of E and E for the divergence of E. Keep these terms in your mind. This is called the curl of E. This is called the divergence of E. It is a dot product. We call it's a divergence. If it is a cross product, we call it as a curl. And uh, if the last part, if equals, sorry, if is the divergence of curl of E. Can you do it? Maybe I'll give you some homework. You can do this curl of E and divergence of curls of E.
हाँ बंगू
अरे D इकाई F इकाई करा. Do it please. Hasan, is that clear?
Sir, D, E, F. Is that all?
No, only D and F.
D and F. Okay,
D
sir.
and F in the class. The other parts can be done and submitted to the Google Classroom before the next class. Please do it and tell me the answer. I will come up within 5 minutes. Have you done this? Have you done this? Awesome.
Yes, sir.
Yes. Good. I will do it for you. And Hasan, can you share your screen paper?
Okay, sir.
Should I make you host to do that? I think no.
No, sir.
No need. No. Hasan, let's make Hasan pin. Not clear. Uh, yes. Okay. What is the divergence? Divergence of curl of it?
0, sir.
Huh?
0.
0. Right. Okay. Very good. Very good. Uh, right. Hasan, help me. What is E? What is E?
So 3xi
3
5
I
5x squared by j
5 x squared y j
minus
minus minus 9
9xz
x z
minus 3z squared k
3 z
square k.
z squared c squared k. If you need to get the curl of E, we use to get the indices. Uh, I j k double upon double x double upon double y double upon double z. This is 3x 5x squared y 9 xz minus 3z squared. So this is the I. We have to operate this one and this one minus the operation of this one and this one. J, the operation of this and this minus operation of this and this. K, operation of this and this minus the operation of this and this. So what is the answer, Kasul?
minus 9 z j
Is
plus
it
10
9 is it plus
9 z j plus 10 xy k
j plus
10 xy k
10 x y k. Okay, there is no I part, no. I mean, there is no vector in the x direction. Right. Next is uh, divergence of curl of E. Did you do it, Kasul?
yes sir.
Okay. Uh, what is the answer? Lambda upon lambda x I plus lambda upon lambda y j plus lambda upon lambda c k dot dot minus 9 z j plus 10 xy k. Uh, so I j dot product is 0, and j to j product remains in double upon double y minus 9 is it. K to K product is also remain. Double on double is it 10 xy. So these are independent variables when there is no relation, and as I told you, for the partial derivative with respect to someone, we have to consider the other terms are constant. Then the derivative of a constant is 0. 0 plus 0, answer is 0. But I need to ask a question from you. If a dot product is 0, what is the meaning of that? If a dot product of something is 0, what is the meaning? Huh? Students? Puzzle? Puzzle?
Sir,
If a dot product of something is 0, what is the meaning?
uh,
So,
they
uh,
are perpendicular.
let's consider two vectors A and B. A and B.
They are perpendicular to each other.
Yes, very good. They are perpendicular with each other. If the dot product is 0, they are perpendicular with each other. Then here it is 0. Then what can you say? So, sorry, it is E, no? E. Am I correct?
No sir. Grad.
Yes. Right. Uh, and the E is also to be 0. You can check this because J is this 5 and K this here is to be 0. No, this is not 0. This is 0. This is not 0. What is the meaning? Curl of some vector is normal to the surface. If there is a vector field, the curl gives the normal vector component to that surface. Curl gives the normal vector component. Is that clear, Kasun?
Yes, sir, clear.
So it's a lifetime lesson in the electromagnetic field theory and the vector analysis. Curl of any vector field. This is E vector field. Curl of a vector field is normal to the surface. Right, I will wind up from here and I will upload this video to my YouTube channel. You can go to the YouTube channel and check it. Okay, have a good day.
Thank you, sir.
Thank you, sir. Good day, sir.
Thank you, sir.
Please upload the rest of the examples to Google Classroom, right?
Okay, sir.